So number 3, part E. I ended up making this a bonus and not like counting it against you if you didn't get it, because it was just kind of hard and not a lot of people got it right, but that's okay. But so it asks for the normal force exerted on the apparatus by the table while the blocks are in motion. So that's kind of a hint while the blocks are in motion. It's actually not equal to the normal force that would be there when everything's just sitting at rest, which would just be the weight of the whole thing. What you can do to figure it out is, if you think about, okay, so this is the stand that's actually in contact with the table, and we're trying to get the normal force between those two. So the normal force has to support the weight of the stand. It has to support the weight of the pulley that's directly connected to it. But then your two hanging masses, what's really going to happen as far as the pulley and how hard those are pulling on it, when those are moving and accelerating, the tensions in the strings are not equal to the weights of those. We found the tension in string 1, so that's this tension on this side, and we can find the tension in string 2. Those tension forces are how hard the blocks will be pulling down, and that's what matters as far as the normal force having to cancel that out and hold everything up. So to get that normal force, what we need to do is add the weight of the stand, which would be 4 mg, weight of the pulley, which would be 3 mg, and then the two tension forces, so T1 pulling down on the pulley and T2 pulling down on the pulley. So T1 we just found in part D, it was 11/9 mg. Now T2 we can find, I'm running out of room here, but I need to add T2 to this. I had an equation earlier in part C for T2 where we had that T2 has to equal 2 mg minus 2 ma. So what you can do is, let's put T2 there for now. You can take your A that we got earlier, which was 2/9 g, plug that in and find T2, and then you can plug that in for T2 here, add everything up, and get the total normal force. And like I said, it doesn't equal the total weight of everything. That's because I know it kind of seems like it should, but because these are accelerating, so these two masses are accelerating, and they're accelerating at the same rate, but this one is more massive than this one. So what that means is the center of mass of this whole system is actually getting lower, because you have them accelerating at the same rate, but the heavier one is, well, it's heavier. So it's like moving the center of mass more than the lighter one is. And so your center of mass is actually moving down. So like the center of mass of this whole thing is accelerating downward. So it's not like in equilibrium. So the forces on it aren't balanced. So the normal force is actually not equal to the weight of the whole thing.